Okay, so let's get started. We were to the point where we're discussing this theorem. Suppose f from some ball into the complex numbers is holomorphic. Then f has a primitive. On the ball. And I gave you a kind of idea how to start the proof. So what we did was we said, okay, let's make the ball centered on 0, and the radius is unimportant. It's always the same. I mean, it doesn't matter for any of the details of the proof. And if we take any z, then we can create a contour that goes like this, which goes along and then up to our z, and we can call that the contour gamma of z, right? And if we chose a different contour that went up and then along, it would make no difference, because we know that if we integrate around the rectangle, it's equal to 0, because that's the theorem we just learned, right? Just before, yeah, because that's just applying Gauss' theorem for a triangle on breaking up this rectangle like this, yeah? Cool. So we can indeed define such a function. I have a proof over here. What does it? Yeah, let's put proof here. Define, well, for any z, define a curve as shown, and then define capital F of z to be the integral over the curve like this. And let's call this zeta. Okay, so and my suggestion for you last time was that you think about how this thing can form a primitive. Did you do that? Do you have any ideas? So we're going to have to show that. So that the limit as h goes to 0, f of z plus h, firstly we want this limit to exist, and we also want it to be equal to little f. Well, any ideas about that? Okay, well, let's take a look. So let's blow up this picture onto a larger scale. So we take our little h going in any direction. Let's say this here is our point z plus h, right? And let's blow up what we see here onto something much bigger. Well, actually, let's just blow up. Okay, let's do this in a couple of stages. Let's put z here, so it's out the way. So this is the point z, and say this is the point z plus h. Okay? So, if we take the contour that gets to z plus h, what does it do? It goes along like this, and then it goes up like this, right? This is this contour. Yeah? And the contour that gives us capital F of z goes along like this, and it goes up like this. Yeah? So, if we just consider this quantity, capital F of z plus h minus capital F of z. Okay. Then what is that? Well, that is the same as going up like this, yeah, minus the contour that goes up like this, yeah? But minus z is like going down and then across, yeah? Yeah, minus z is like going down and across, yeah? Because we've learned that if we do a contour in the opposite direction, it's minus what it was in the previous direction, yeah? Cool. So if we go down and across, and then we add f of z plus h to it, it means going across and then up, yeah? This part here is going to be wiped out because we're going this way and then back across it, yeah? Do you see what I mean? So what this means is that capital F of z plus h minus z is like what happens when we go down, across, and then up like this. So we integrate little f on this contour. That's exactly what capital F of z plus h minus capital F of z would be, yeah? And then we could, instead of doing that, we could say, okay, what if we considered the rectangle formed by going across like this, yeah? Yeah? So if we consider the rectangle formed by going across like this, we know that the integral of little f over the rectangle defined like this is 0. That's the theorem we've discussed, yeah? So that means that going around like this, yeah, has to be the same as just going like this. Just going like this. Is this picture large enough for you? Shall I make it bigger? Put your thumbs up if you can see it. Okay. So once again, since going around like this, integrating on all these four sides, gives us 0. Yeah. If we just did 3 of those sides, yeah, and then added this side, it's 0. Yeah. Which means those 3 sides is the same as negative this side. Yeah, and negative this blue side is the same as going in the opposite direction. Put your thumbs up if you are with me here. Okay, cool. So when we're doing this contour this contour integral that gives us capital F of z plus h minus capital F of z, instead of going around these 3 sides all the way up to here, we could instead just decide to go from here across and then up to this. That would be the same thing. Yeah? Because once again, going across like this is the same as going like this. Cool. So we have, let's blow it up over here, we have that this thing is equal to what happens when this thing here is z, and we go across like this, and then up like this, to this to z plus h. Yeah, that's what we've learned. Yeah, so if we integrate on this contour with little f, that's exactly what this thing is. Yeah. Now, consider the rectangle formed by doing this. Yeah. If we go down like this, then integrating over this rectangle with little f gives us 0. That's Cauchy's theorem. Yeah? Which means that if we integrate like this, yeah, and then plus this blue side, it's equal to 0. Yeah? Which means minus this blue side is the same as integrating across like this and then up like this. And minus this blue side is the same as going in this direction. Yeah? So what this picture just shows us is that actually this quantity is the same as directly integrating from z to z plus h, yeah, in a line. Yeah? Cool. All right. So what that means is that we can explicitly write out what this thing will be as a nice simple contour. Right? So we've just shown that this thing is equal to the integral of the line segment z to z plus h. And I'm going to put this arrow here. Maybe it's not necessary, but just to indicate we're going from z to z plus h. Yeah? And f of z, dz. Not z, because we've used zeta. That's what we know. Yeah? Thumbs up if you're with me. Cool. All right. And this thing is an easy thing to calculate because we can just put a parameterization for this little line segment here. So let's say z of t is equal to z plus t times h for t belonging to 0, 1. Yeah? So z of 0 is equal to z, and z of 1 is equal to z plus h. And so this thing, let's call this thing star. So star, we're going to write out this parameterization, is equal to the integral from 0 to 1, f of z of t, z prime of t dt, and let's see what that is. That is the integral from 0 to 1, f of z plus t times h. And then when we take the derivative of this thing, it's very simple. It's just h, right? dt. That's what we get. Yeah? Cool. So that is our thing that we're trying to understand. Let's erase this thing. Doesn't matter. So f of z plus h minus f of z over h. We divide by h. This h is not part of the integral. We just pull it out, right? It's just some complex number. So then this thing is just the same as the integral from 0 to 1 of little f of z plus t times h dt. Yeah? Cool. So if we want to look at the difference between f of z plus h minus f of z over h minus little f of z, okay, well, that's the same as the absolute value of the integral from 0 to 1 of this guy, f of z plus t times h. And now let's just put this f of z right inside like this, okay, dt. Because when we integrate just this fixed complex number, f of z over 0 to 1 with respect to t, it's just f of z. Yeah? So we can just put it inside the integral. Yeah? And let's put the absolute value signs outside like this, or inside like this. We have this plus t times h minus f of z like this, dz. Yeah? Cool. So what is that? What's that quantity here that we're integrating? Well, let's put a little bit of space. So we have z, and we have z plus h, and this thing is just some point along this line as t goes from 0 to 1. Yeah? And f is differentiable. Yeah? F is differentiable, so in particular it's continuous. So as h goes down to 0, yeah, then f of z plus t times h has to tend closer and closer to f itself, right? Yeah, for any t between 0 and 1, right? So again, this thing is just some point along this line. Yeah. So this would be where z plus t times h would be, say, yeah? And since we have continuity, then the difference between little f of z and little f, in fact, inside any ball, right, of radius h is going to go down to 0. That's what continuity means. Yeah? So this entire expression here is going to tend to 0 because we can guarantee that this stuff inside the absolute value signs is less than epsilon, yeah? So long as we insist that that little h is small enough, just by continuity. Yeah? So since this is less than epsilon for every t between 0 and 1, then as we integrate over 0 and 1, the entire thing is less than epsilon. Yeah? So that guarantees that as little h goes down to 0, this quantity has to go down to 0 as well. Yeah? In other words, we have exactly got the limit of this thing is equal to this thing. What did we use? We just used this nice property that we learned that if we integrate around a closed rectangle inside this ball, it's equal to 0. Yeah? And that if we integrate across a triangle, it's equal to 0. We just use Gostad's theorem. Yeah? So Gostad's theorem allowed us to turn this somewhat complicated looking thing, right? Which we went, when we consider f of z plus h minus f of z, it's like going up like this and then plus going down like this, yeah? Yeah? Which we know is the same as going down then up, yeah? Yeah? Which is the same as just going across then up, yeah? Which is the same as just going in a direct line like this. Just by using Gostad's theorem again and again to just reduce it. Yeah? Okay. So after this class is over, a good idea is to just try and draw the pictures to convince yourself of this reduction to understanding f of z plus h minus f of z, yeah? Just in terms of integrating little f from here to here. Convince yourself that it reduces from this to this from these pictures, okay? Because that's basically the heart of the proof, yeah? And then this stuff is kind of, once you're here, you know you're in a good shape because you write down the expression and you divide by h, you have exactly this, yeah? And so this thing minus this thing for sure is going to tend to 0. And you're all set. Cool. So we have that this is true, that any holomorphic function has a primitive on the ball. Yeah? Cool. All right. Now I keep saying that complex analysis is calculus in the complex plane, but that it diverges dramatically. What about this theorem? Is there an analog to this theorem when we just consider real valued functions into R? What would be the statement of the analog for real valued functions into R? What's a ball in the real line? So the analog would be if we have a differentiable function in the open interval, it has a primitive. Is that true? Is that true, people? I'm going to raise the board. You guys think about this. Give me an answer before we get going again. Yeah, the answer is indeed yes. And what's the theorem that gives the answer? What theorem what theorem are you using to tell me the answer is yes? Into part 1, right? Do you know what the antiderivative is? So given some f from an interval a b, and indeed it only has to be continuous, f into r, which is continuous, then it has a primitive. And what is the primitive? Can you tell me what it is? The derivative of g is equal to f. Well, let's take a look. If we have, this is where we start a, this is b, let's take a function f like this. Let's take t, right? Bad line. So this G represents what I call the increasing area, right? If we have a positive function, yeah? So if we take, actually let's call this thing X instead, X, and if we move forward to X plus H like this, and we look at this thing, okay, then G of X plus H minus G of X is exactly this strip here, right? It's exactly this strip here, yeah? So if we try and get some idea of what this quantity is, it's the area here, right? The thinner this thing is, right, which is the same as saying the smaller H is, the more this thing looks like a rectangle, yeah? Whose base is H, yeah? And whose height, well, what's the height? Well, this thing is f of x, right? So its height is kind of like f of x, right? It's kind of like f of x. Because this is x, this is the graph of little f. So this point here is f of x, and on this picture it's moving up a little bit, yeah? But basically the height is f of x. Or if we take f of x to be the height, then the difference between the height and f of x is just this stuff here, right? So we can approximate this area, we can approximate this thing. This thing is approximately equal to just f of x times h, right? Plus or minus this little red stuff here, yeah? And this little red stuff here, what's the area of that? It's something like h times a constant, right? Yeah? So plus or minus some error constant times h squared. Yeah? So if we do g of x plus h minus g of x over h, it's just f of x plus or minus a constant times h. Yeah? And we take the limit, we just get f. Yeah? So this is the fundamental theorem of calculus part 1, and it follows very easily just from pictures, right? Yeah? And the fundamental theorem of calculus part 2 follows immediately from this, just from the fact that if we have two antiderivatives, they differ by a constant. Yeah? So then we, yeah, okay, I don't want to completely redo the proof, but this is true. This is a true fact, and it's an easy fact, and it's a life-changing fact because it means that we can calculate all these definite integrals, and it's just a simple picture. All right, that's from calculus. Now we have the analogous thing is true, but with the stronger hypothesis that f is differentiable. Yeah? Cool. So let's talk about some corollaries to this. So corollary, if gamma, it's not going to like this, gamma is a closed curve in omega, not omega, in the ball, and f is hollow in B, then integral of gamma f of z dz equals 0, just because it has a primitive, right? So we started off proving that if we have a triangle, then it's the integral around this is equal to 0 for any triangle containing a holomorphic domain and a domain omega where f is holomorphic. Now we know that we can have any closed curve at all, so long as it's inside the ball, and that's equal to 0. Yeah? Cool. So we are going to need to have a little extension of this theorem that there exists a primitive. And Stein has this stuff about toy contours, and I want to be a little bit more explicit than that. So I'm going to define a class of domains for which this theorem holds true. Okay, we'll define them as follows. So, given this subsetting some nice class of domains. So let k be some integer, and we are going to take delta to be 2 to the minus k, and we're going to define a bunch of squares that cut up the complex plane. So define squares. Let's define them like this. Q, K, no, let's not use K. What do we use this? Let's call this N then. Q, K, L. And let's put a delta here. Well, no, just consider delta be fixed. Q, K, L to be this thing. So let's go like this. K to the minus 1 times delta, K times delta, cross product I, and then L to the minus 1 times delta, L times delta. All right? So the picture is better than the math. We are just cutting things up into delta side length squares, delta side length closed squares. Yeah. And obviously the union of all of these as we run from k and l over all integers gives us everything inside the complex plane. Yeah. And it's a countable collection of squares, so we're just gonna define okay, now I'm going to put back the delta. Define let's define the S delta of M for M belonging to natural numbers to be just this collection. Q delta L K L, where K and L belongs to Z. In other words, we're just putting a numbering rather than have to deal with two indices, which will be annoying. I'm just renumbering them in any way for all M belonging to natural numbers. Right? So this one could be the first one, this one could be the second one. I don't care. Yeah? I can just renumber them and just create this collection like this. Yeah? Everybody happy? Okay, so we are going to define a following domain. We say omega is rectangular good. Maybe I should call it dyadic good. Dyadic good would be a better name. Dyadic good. If and only if omega is the union over all M belonging to I of some collection of these guys for some, or omega closure for some I, which is contained within natural numbers, some subset, and some delta bigger than 0. And this is the key point, if we consider the complement of I, so consider the union of every M belonging to the complement, then this thing is connected. Okay. Okay, again, better. The pictures are easy to understand. This is the language. Now let's talk about what this actually means. What this means is that we have this set, which is made up of this union of little squares like this. Okay, something like this, whatever. Like this, whatever. And if we take the complement, it's connected. So we can't have something like this. We can't have these squares doing something like this, where there is like an empty hole in the center. Because then the complement would contain this stuff and everything out here, which is not connected. No? So the point of this is that we have some set which is made up of the union of some little squares where when we take the complement of it, it has no stuff inside. In other words, the set has no holes inside it. Yeah, the set has no holes inside it. Yeah, that's the point of this. And later we'll talk about a concept called simply connected. And what this is a crude version of a simply connected set. So we want to avoid talking about simply connected and topological concepts quite yet. We want to go further into the theory, prove stronger theorems about functions. But what we're doing now is developing or describing a class of sets that is simply connected, because we're later going to find out that simply connectedness is an important property that allows us to prove many theorems, but it's a property we definitely need for this generalization of the existence of a primitive that we're about to prove or about to describe. Okay, so everybody clear on what this is? It's basically a collection of closed squares, such that it's going to be connected. I should also say that I should actually add that as a property. So this is this, and the actual union is connected, such that it's connected and its complement is connected. i.e., omega contains no holes. All right, so I'm going to erase the board, and then we're going to state this theorem. Okay, theorem. If F is holomorphic on omega and omega is dyadic good, then it has a primitive. Okay, this I'm going to set as a homework problem, but I'm going to give you a hint as to the issues. So what do we have? We have a dyadic good domain, so it has no holes. Yeah? And how did the proof work previously? So let's do something like this. I could do this like little squares around here to make this look like it's dyadic, whatever. I don't want to draw it, but the point is that it has no holes. Yeah? So the issue, or the way this worked before, was that we took some path from some point to z, right? And some sort of rectangular path, whatever, like this, yeah? And then we said, okay, we have this stuff about if we move off to some little point here, z plus h, then the quantity f of z plus h minus f of z reduces down just to a line segment connecting z to z plus h. Yeah? And that stuff is like a local argument. Yeah? It's a very small h. This is an open domain. So that particular stuff about arguing around here, that stuff is fine. Right? That stuff is fine. The issue is making sure that when we define a capital F from this path like this, that it is actually well-defined. That it's actually well-defined. Okay? That's what we have to think about. In the case when it was a ball, that was really trivial, because if we do this, or we do this by Gauss-Stett's theorem, or Gauss-Stett's theorem generalized to a rectangle, then it's well-defined. It makes no difference. Yeah? But in this case, we have to think about it a little bit. We have to think about it. Yeah? So whatever rectangular path, if we take a rectangular path like this, or if we take a rectangular path like this, yeah, it's got to be the same thing in order for this function to be well-defined. That's the stuff we have to think about. Yeah? Cool. So that's going to be your homework exercise. I'm going to ask you to come up with a proof of this. I'm also going to ask you to tell me why this isn't true unless we have this assumption that the set has no holes. Okay? All right. So after you do this, then I'm going to talk about how to do this if you don't give me complete enough solutions. But all right, let's assume or prove hint is this picture here. Okay. All right, so with this thing, we can now, let's talk about keyhole contours. So keyhole contour is when you have something like this. If you have a ball like this, and if we decide to go inwards and then do a little ball like this and then go outwards, this is a keyhole contour. Okay, this is a keyhole contour. And I guess I'm not sure why it's called a keyhole contour. Yeah, I mean, I guess this looks a bit like a keyhole, right? Apart from these lines going in and out like this. And the point of this thing is that it's a nice closed curve. Yeah, it's a nice closed curve. And here is a theorem. If f is holomorphic this is actually the only kind of keyhole contour we're going to use. So let's make this outer radius r and this inner radius little r. I guess you can't see that. This is little r. And if f is holomorphic on omega, and let's make this little thing here delta, just to be really concrete about it. And if this is how we define a keyhole contour, then it's defined by these things. So let's let x be the center of this thing. So the keyhole contour is defined by the center, the radius of the inner circle, the radius of the outer circle, and then delta. Yeah? So if F is holomorphic and omega contains the closure of the interior of a keyhole contour. I'm not going to put all the indices, I'm just going to write this. Where gamma is a keyhole contour. Then integral around the keyhole contour f of z dz is equal to 0. Okay. So more generally, a keyhole contour is just any shape where we do this kind of thing. We go inwards with the little narrow strip and then do a circle and go out again. But for the time being, we only care about when we're doing it where the outer circle is a circle. So I put these parameters on so you have a concrete idea what it means to talk about a keyhole contour. All right, so this is our theorem. So we have some domain, whatever it is, whatever our domain is, and it contains the closure of the interior of a keyhole contour. So we have a keyhole contour like this. Okay? It contains the closure of the interior of a keyhole contour. And our claim is that this thing, therefore, the integral of this closed curve is 0. All right, tell me why that's true. Why is that true? I'll draw a bigger picture of a keyhole contour to help you. So, this is the keyhole contour, right? We have the interior plus the boundaries contained within our set omega where f is holomorphic. Why is it the case that we can just integrate around this keyhole contour, have it be 0? But what we can do is that we can have a dyadic good domain that contains this thing, right? And it's still going to be inside our set omega, right? Yeah? Yeah? So for example, if we just take some very, very small delta, or we already chose delta. Let's choose alpha, which is less than delta over 100. Yeah? And then just cut up the plane into all these squares of side length alpha. Yeah? Yeah? And then we just take all the ones that intersect. So I'm doing this not very well, but all the ones that intersect the interior of our keyhole. Yeah? Then if we take alpha sufficiently small, what are we going to get? We're going to get this thing, right? This thing, which is the union of squares, where this union is connected, right? Can you see what's happening here? The union will be connected, and the complement of all these squares will also be connected. Yeah? Cool. So for sufficiently small, and this might not be small enough, whatever, let's just write this. For alpha, which is way, way smaller than delta, and alpha has to be 2 to the minus k for some k, because we've cutting things up this way. Yeah, we get that this thing is contained within a dyadic good domain. Yeah? Just from the pictures. Put your thumbs up if you can see that. So what we're going to do, let me actually write down some words. So let alpha equals 2 to the minus k be much smaller than delta. Okay, and let I be the set of all k such that these squares of side length alpha k intersect the interior of the keyhole contour is not equal to 0. Yeah? Those are all the squares that I'm drawing here. Yeah? Yeah? And if alpha is small enough, we see two good things happen. Firstly, there is not going to be any filling up of this gap between these lines. Yeah? So that means that the complement of all of these guys will be connected. Yeah? We can go from any point here to any other point. Yeah? It's just connected. Yeah? And it's also going to be the case that since the interior of this thing is connected, then all of these guys, or the union of all these squares that intersect the interior, that'll also be connected. Cool. So this guy, maybe let's call that alpha 2 just to make the dependence. Then, for small enough, the union of all of the guys inside I of alpha, S alpha k, these things are closed squares, is connected. And the union of everything which is not inside these guys is also connected. Are you all with me here? Put your thumbs up if that's making sense to you. Here's a metaphor. So you know when you're buffering something, when you're loading watching Netflix, and then it takes a while for your internet to get all the bytes, and it does this kind of pixelated version of your picture, right? Pixelated version of the image. So imagine having a pixelated version of this keyhole contour. Yeah? Then what that is nothing other than this thing, the union of all the squares that intersect them. Yeah? And we can take the pixel size smaller and smaller and smaller so that it looks incredibly like the actual keyhole contour itself. Yeah? Or keyhole contour and its interior itself. Yeah? So therefore, it will be an open set. It will be a connected set. Yeah? And the complement of this set will look incredibly like the complement of the keyhole contour and its interior. Yeah? So it'll have this property that it's connected because the complement of a keyhole set is a complement of a keyhole contour is connected. Does that make it better? Because we can make this alpha as small as we like. All right, cool. So we have this. Okay, we have this. So take this union of all of these guys, I alpha, sk, this thing. Yeah, and let's take its interior. So let say pi is equal to the interior of this thing. Okay, the interior of this thing. Then, by definition, pi is a dyadic good set. Yeah, and by the previous theorem, there was a primitive. Yeah, so there is a primitive. And therefore, we are integrating a closed curve around a set for which there is a primitive, and we know it's 0. Yeah? Cool. So we have that if we have an open set, okay, where there is a keyhole contour inside the set, yeah, then we actually have that the integral around the keyhole contour is equal to 0. Yeah? And because we've slightly extended the domain that we're interested in by letting this dyadic good set be just the union of all the squares that intersect this keyhole contour and its interior, yeah? We don't care about omega having any properties at all. Yeah? We don't care about that. Doesn't matter. Yeah? Because we've just restricted the game to being the keyhole contour and a little bit outside of it. Yeah? Cool. All right, so now I'm going to use what keyhole contours are good for. Cauchy integral formula. I'm going to abbreviate this to F because it's so fundamental. Okay, so what does this say? Suppose we have F from omega into this thing. Omega is open as always. Omega is open. So I'm going to forget to say that sometimes, but we're always going to be talking about open omega. And F is holomorphic on omega. Then, what do we have? We have that if the ball B R of Z0 is contained within omega, then F of Z is equal to 1 over 2 pi I, the integral around the boundary of the ball around Z0 of F of zeta, zeta minus Z, like this, the zeta. Okay, so first time I saw this, I was a little bit nonplussed because it looks kind of a complicated formula initially. Let's point out a few things. Firstly, we have Z0, this is radius r, but this formula holds true for any z inside this, so not Z0 itself, but any z. So what we're doing is we're integrating around the boundary of the ball, like this, yeah, and considering this expression right here, yeah, and it turns out we get this thing. And as you're aware, if we integrate something, it's a regularizing thing, right? It makes things nicer to integrate things, yeah. Whereas if we differentiate, typically things get worse, they get more complicated. So when you have something where you can express your function at some point in terms of integrating around your function or on something else, that is a very regularizing property. And that's a very strong property, and that's what we're going to see later on. So there's going to be a host of corollaries from this formula right here. Yeah. Before we go into it, though, I want to try and illustrate what it's saying. So we're going to do this in the following way. So what is this saying? This is actually one of the key theorems of the entire course. All right, let's take the very special case when we just put Z equals Z0 at the center, okay? Take Z equals Z0, yeah? So then this formula was like this, and let's write out actually what this actually is, okay? So let's put in the parameterization and see what we get. So that means as a special case, we have this theorem, we have this true fact, f of zeta minus z0. Okay, and let's put a parameterization in. So let's take z of t equals z0 plus t plus r. E to the it. Okay, then z prime of t is equal to I r e to the it, like this. And then what does this formula say? Star. Then star says that f of z0 equals 1 over 2 pi I. And now we're going to integrate using our parameterization. So we integrate 0 to 2 pi. And then this is f of z0 plus r e to the it. This thing here, because the way you find this thing here is now going to be just r e to the it, like this. I should put zeta, since we're doing respect to zeta. Yeah. And z prime we've calculated, it's this, it's just I r e to the I times t, and now we're integrating dt. Yeah? So all we've done is use the definition of integration on curves with this specific parameterization. Yeah? And then we see that we have some cancellations. This cancels with this. Yeah? And the I will cancel with this. So what this gives us is just, oops. Is just this, 1 over 2 pi, integral from 0 to 2 pi of f of z0 plus e to the it dt, like this. Yeah. Everybody happy? Oh, but this is wrong. No, this is correct. Everybody happy? Cool. All right, let's write out what this is. This is 1 over 2 pi, integral from 0 to 2 pi. And let's break this up into the real and imaginary parts. So the real of f, integrated like this, z plus the it, plus the imaginary part of f, z plus r e to the it, like this, dt, and let's break up the integral. That's 1 over 2 pi, integral from 0 to 2 pi of the real part of f, z plus r e to the it dt plus I times 2 pi like this, I times 0 to pi imaginary part of f, z plus r e to the it dt. Yeah? Cool. Now, let's write this like this. Let's do this. Let's write this thing as 1 over 2 pi r, integral from 0 to 2 pi. Actually, I want to rewrite everything. Let's just adapt the previous formula. I'm going to write this as 2 pi r, and I'm going to put an r in here. I'm going to write this as, I'm going to break this up, and I'm going to write this as plus I over 2 pi r. And And I'm going to put an R over here. dt. Okay, so the stuff in the brackets here is now just a real integral, i.e. an integral of a real valued function over a curve. Yep? Yep. And what is this R? Well, this R is the absolute value of the derivative of the parameterization. Yeah? Yeah? So I can replace this R just by absolute value of z of t, or z prime of t. So this thing is the same as absolute value z prime of t dt, and the same thing here. This thing here is absolute value z prime of t, like this. Yeah? Give me a thumbs up if you're with me. Okay, so, cool. So, what does that mean? Well, if we look at this expression here, right? What are we looking at? What kind of integral is this thing here? What kind of integral? It's the integral around a curve, right? Yeah? And we're using our parameterization z, yeah? So this thing is nothing other than 1 over 2 pi r, and then we're just going to write the integral around the boundary of the curve, the r of z0, the real part of f. And if you did multivariable calculus, you probably saw something like ds, or something like this, to indicate it's a one-dimensional line integral across the curve, right? But later you're going to learn that there's a correct notion for this, which is called Hausdorff measure. And this is one-dimensional Hausdorff measure. So I'm going to write this thing like this. This is what this thing is over here. It's the one-dimensional integral of a real valued function over a curve. Yeah, what you learned from multivariable calculus. Yeah? Do a recap over here. I'll complete the expression first of all, and then I'll put the recap. So that's this thing, and this guy is this. The same thing, right? It's 1 over 2 pi r, and then it's the integral around the boundary of this thing, just this thing, this imaginary function, or the imaginary values of f. And then I'm going to write the h1 of x like this. Okay, that is what this thing is equal to. Now here's a little recap on integrating on curves from multivariable calculus. So given curve gamma contained within R2, right? Then you've learned that if z from A to B into gamma is the parameterization, then length of gamma is equal to the integral from A to B z prime of t dt. You guys all know that. You people all know that, right? And in fact, I get a little brief sketch of that in this class, right? And then from that, it's pretty easy to see that if we actually integrate a function over the curve, so we have some function f defined on our curve gamma in R2, then the way to do that is as follows. So the integral over the curve gamma, f, right, the h1, is the integral from A to B of f of z of t, z prime of t, dt. Yeah? And when f is equal to 1, then that thing is just the length of the curve. Yeah? Yeah? So that stuff should be recap for you. Yeah? And if it's not, go back in your multivariable lecture notes and then look again at this, and you'll see that this is true. And this formula is natural because the point of this absolute value of z prime of t is to take out the scaling from the expression. Okay? Yeah? Takes out the scaling from the expression. Because we want this thing to be independent of whatever parameterization we've chosen. Yeah? And this factor here takes care of that for us. Yeah? Cool. Is this coming back to you people? A little bit? And if not, again, look back at multivariable calculus. We can look at our multivariable calculus. I'm happy to answer questions about multivariable calculus if anything's unclear, because we need that stuff. And that is all we're doing here, right? That's just what we're doing here. We have a real valued function. Yeah? We have a parameterization around a curve in the plane given by z. Yeah? So this thing is the same as this thing. That's what a real valued function defined on a curve in the plane is defined to be. Yeah? And the same for this thing. Cool. And then what is this thing? 1 over 2 pi r. That is just the length of the circle, right? Of radius r. So this thing here is actually the average of the real part of f over the circle of radius r. Yeah? And the same for this. This is the average of the imaginary part over the circle of radius r around z0. Yeah? Yeah? Sometimes, well, not sometimes, we have this notation. This thing is the average of f. Stay for a second. This thing is defined to be equal to the integral from a to b of f dx over b minus a. This is the average. This is common notation. So I could just write this like this. This is the average of the real part on the circle plus I times the average of the imaginary part on the circle. Okay? So, if we believe Cauchy integral formula, what it's actually saying in the special case when we say z to be equal to z0 is that f is equal to this thing, the average of the real part of the circle plus I times the average of the imaginary part on the circle. Yeah? And since f itself is just equal to the real part at z0 plus I times the imaginary part at z0, yeah, it's therefore saying that this thing, is equal to this thing. And this thing is equal to this thing. Yeah? And when you have a function where if you integrate around the boundary of the circle and you end up having, you integrate around the boundary of the circle and you divide by the length, that thing is just the same as the value of the function at the center of the circle. That thing is called the mean value property. Yeah? So let's think about what that says. If we have a function that satisfies this, it means that, think of a function from R2 into R as a mountain landscape, right? That means whenever you take a point, you take some circle around the point, and you take the height of the mountain as you move around the circle. So sometimes it's up, sometimes it's down, but the average of the height around the circle is the same as the height in the center of the circle. That's what it means. Yeah? It's a very particular, very specific property. Yeah? That's the mean value property. Yeah? So part of the Cauchy integral formula, when we just look at what it says when z equals z0, and we look at what it says for the real and the imaginary parts of our function f, it says that they have this very specific property, the mean value property, that when we average around the boundary of a ball, the value is exactly equal to the center. Yeah? Which to me is much more meaningful than this expression right here.